we're actually going to learn some new rules that are going to make this really nice, okay? So a lot of what we've been leading up to seems like, holy cow, I mean, it's a lot of work, a lot of groundwork, and some of the things can be very tedious. So if you got done with the stuff in 2.8 like I asked you to, you found the derivative of lots of different functions the long way. You did it from the definition, the limit of the difference quotient. And that's a very valuable thing. That is where these things come from. Today we're going to start learning some rules that will make these much, much quicker, okay? The derivatives that we've spent for the last couple of days, maybe spending 5 minutes finding, you're literally going to find in about 10 seconds, okay? All right, so let's take a look here. I've got a starter question on this one. We want to rewrite this expression right here. And remember I said most of the time we're really good at simplifying things. We're not very good at making things more complicated. So this is a nice expression. Okay, this could have been an answer in an algebra class, but we might be interested in making it look more complicated. So the first thing we might do is break this into two fractions. So I'd make this 2x over 5 and 3 over 5. And I could even make it more broken up. I could pull the 2 out front, and I could have an x over 5 here, and then a 3/5. Or I could do something that would be really silly. That looks reasonable enough. What if I did this? Had the x out here and the 2/5 there. Okay? Any one of those would be fine. Okay? But just keep in mind that oftentimes, in order to make something work out algebraically, we're going to have to do something that's a little bit counterintuitive, opposite of what we normally do. We might want to make something look more complicated for the time being so we can eventually get it to something that we can recognize, which is what the next starter question is about. What do we call this limit? If you ever see this, what is this?
It looks like one that's differential equation.
Okay, it looks like the difference quotient. It's a limit of a difference quotient. What function is this? I'm not really asking a trick question there. It's got a name. It's called u. The function is u. So this is literally, if you go back and look at the definitions for the derivatives, all this is instead of f prime of x, this would be u prime of x. That's it. So if you ever saw something that looked like this, which will happen quite often when we're looking at proofs, looking at definitions, if you see something that looks like this, it would be u prime of x. You can take this entire mess right here and say, I know what that is. That's u prime of x. So if this were a w instead of a u, it would be w prime. If it were a g, it would be g prime. Okay? So again, a lot of times we're not trying to do anything ridiculously complicated. Okay? We're just trying to recognize things that look a little bit more familiar. Okay, so again, this section is going to have a bunch of rules for finding derivatives, and we're going to start out with what's called the constant rule. So if we've got a function that's a constant, then its derivative is 0. Now, if we write this in prime notation, f prime of x would be 0, okay? Or the derivative with respect to x of a constant is 0. So if we say this in words, the derivative of a constant is 0. It's that plain and that simple. So if I have y equals 5, what's y prime? 0. If I have f of x equals negative 2, f prime of x would be 0. If I have the derivative with respect to x of 7, the answer is 0. And my question for you is, why are these all zeros? Ben? There's no slope. Okay, or a better way to say it is, the slope is 0. Okay, a lot of times we reserve no slope for a vertical line. Every one of these is a horizontal line. So y equals 5 is that line right there. If we're talking about the derivative, if somebody says derivative, we think slope, we think instantaneous rate of change. So what is the slope of this? It's a horizontal line, so the slope is 0. So we'll just say that they are horizontal lines. So they have a slope of 0 everywhere. Okay. So if you ever see a constant, its derivative is always going to be 0. You don't have to go through and do it by definition or anything like that. You just know immediately it's a 0. Okay? We could find it by the definition. That would be a little bit of a silly exercise. So here's the derivative of a power function. So like x cubed, x to the 4th, x to the 99th, or whatever it happens to be. So if you have a power function, x to the n, then its derivative, f prime of x, is n x to the n minus 1. Okay? Or again, in differential notation, the derivative with respect to x of a power function is take the exponent, bring it down, then it'll be x to the n minus 1. So I like to do things in steps. I like to have sentences and phrases that describe what we're doing. Okay? It can be helpful, especially when we're going to undo these in a couple chapters. Okay? So we multiply by the old exponent, reduce the exponent by 1. So I'm going to do one example really quickly, and then I'm going to do a quick little proof. This one's hopefully not too bad. So if f of x is x squared, we already know the answer to this, but let's see if this little rule works. It says multiply by the old exponent, so I'm going to bring the 2 down, reduce the exponent by 1. So if I take 2 and reduce it by 1, I get 2 times x to the first, which is just 2x. Now that literally took, even with me yakking, about 10 seconds. How long did it take us when we used the definition of the derivative, when we used the limit of the difference quotient? It took quite a while to do that. Okay? So here's why. So if I start off with this right here, this is what I have. I'd have the limit as x approaches a. And if you don't want to write this down, I think this is in your textbook. You can just watch and think about it. Okay? So if the function is x to the n, then this would be x to the n minus a to the n over x minus a. Now I'm going to use a little factoring formula. This is from the binomial theorem. Okay, and we can actually take out an x minus a. So if I take out an x minus a out of this stuff, now this is what makes proofs confusing. I don't have a number here. So you have to get used to how to write this. So if I take out an x minus a, this is what I'm left with. I'm left with an x to the n minus 1 plus x to the n minus 2 times a plus x to the n minus 3 times a squared. And that pattern is going to continue. The exponent on the x is going to reduce by 1 every time, and the exponent on a is going to increase every time. In fact, I could put an a right here. If the exponent here is 1 and the exponent here is 2, this would be a 2, a 1, and technically that would be a to the 0. So I could put them on each one of these. So I'm going to put dot, 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 and then I'm going to put plus. This is going to be, let's see, x. Let's see, how do I want to write this? This is going to be, we'll do a to the n minus 2. And then this is going to be a to the n minus 1 all over x minus a. Again, this is the binomial theorem. So, I've got this factor of x minus a on the top and this factor of x minus a on the bottom. I can cancel those off. And then I'm finding the limit as x approaches a. So, what's the variable in this problem when I'm taking the limit? Careful. No, x. X is the only thing that changes. There were 3 choices. You got it on the 3rd one. That's not too bad. Okay? So if we let x approach a, this is going to be, let's see, this is going to be a to the n minus 1. This is going to be a to the n minus 2 times a. Well, if I have a to the n minus 2 times a, I'd add the exponents, so that's going to be a to the n minus 1. If I do it here, this is going to approach a to the n minus 3, add 2 to that, so that's going to be a to the n minus 1. And that's going to happen on every single one of these. So this one's going to be a to the n minus 1, and this one there's no x in it, so it's already a to the n minus 1. And there are n of these terms, and they're all identical, so this would be n a to the n minus 1. Okay, now, not a big deal if you didn't follow all of that. If you want to talk about the binomial theorem and you want me to show you why this works the way it does, I'd be happy to show you a couple of examples so you can see where that comes from. But the point of this is this. Again, don't get caught up in, I don't really understand the proof. If you want to understand the proof, come talk to me. Okay? But you need to be able to find the derivative. So we want to find the derivative with respect to x of x to the 17th. So this process says, if you've got a power function, take the old exponent, bring that down and use that as a factor out front, and reduce the exponent by 1, and that right there is the answer. Now, can you imagine plugging this into either this formula or the limit of the difference quotient, multiplying x plus h by itself 17 times, and canceling off all those terms? It would work. It would probably take you half a day, and you'd probably make mistakes in doing it. Okay? There we've got the answer right off the bat. That is the derivative. You want to know the slope at any point? I'll tell you the slope at any point. If you want to know what it is at 2, plug in a 2 into that, raise it to the 16th power, and times it by 17. That will be the slope on that particular curve at x equals 2. Okay? That quickly. Okay? So these rules are going to come in really handy. Now, is this a power function? Technically, yes. I could rewrite this as x to the negative 1. So keep in mind, the process is bring the exponent down. So we're going to multiply by the old exponent, and we're going to reduce that by 1. Now, don't get caught up by the fact that it's already negative 1. If you reduce negative 1 by 1, what do you get? You get negative 2. So you get negative 1 over x squared. And I believe we've actually found that derivative by hand before. Took one heck of a lot longer than that. And here it just spits out the answer. So if we take a look at this one right here, what's the derivative of x with respect to x? It is 1. So think about this. The exponent is 1. So we'd bring that down. We'd reduce the exponent by 1. So that would be x to the 0. So the answer on this one is 1. Can somebody think of another reason besides the power rule that we just went over of why the derivative of x would have to be 1? Yeah?
Because it has a slope of 1?
Yeah, it's this line right here. It's a perfect 45. Everywhere on that line has a slope of 1. Okay? So this rule matches up with what we intuitively figure out using geometry. Okay, are there any questions? Okay, please take a look at this one. What's the answer on this? The answer on this one is 0. Okay? This textbook, along with plenty of other textbooks, think it's kind of cool to see if they can trick you. Okay, this looks like a power function, but it's not. It doesn't have an x as a base. It's just the number 16, so it's a constant. We default to that other rule up above. The derivative of a constant is 0 because that would represent a horizontal line. It doesn't change at all. If x changes, y doesn't change. And remember, we're finding the difference in y's over the difference in x's, okay, in the limit. All right, so the power rule works even if it's not an integer. So remember this one right here? You went through all that work on the last test in order to figure this out. This is x to the 1/2. The power rule says bring the exponent down, reduce the exponent by 1. If I take a half and reduce it by 1, I get negative 1/2. You could leave it like this, but again, everybody listening? As a general rule, I want you to simplify, I'll say it this way, simplify to a reasonable degree. Okay, this wouldn't be the end of the world if you left it this way, but if you had to use it again, would you want to use it in this form, or would you want to use it like this? If you had to plug something in, think of, gosh, if I had to actually use this, would I want to leave this mess, or would I want it to look like this? That's a lot easier for most people to work with, okay? So the derivative here would be 1/3 x to the, well, let's see, this would be negative 2/3, right? Again, there's nothing wrong with this as the derivative, but you'd probably want to write it this way. 1/3 cube root x squared. That's going to be a lot easier to work with. And remember, you could also do this. 1/3, find the cube root of x, and then square it. Sometimes that's easier. Remember that property of radicals. Questions? Okay, so how would you find the derivative of this guy right here? Yep, so we're going to change this to x to the negative 2/3. There's our function. Now we want to go about finding the derivative. So we'll multiply by the old exponent, so that's going to be negative 2/3. We're going to reduce the exponent by 1. If I reduce that by 1, that's going to put me at negative 5/3. So this would be negative 5/3. So again, nothing wrong with this. This is mathematically correct, but if you were going to use it again, this would again be simplifying to a reasonable degree. negative 2 over 3 cube root of x to the 5th. That's probably the cleanest way to write that. Okay, are there any questions there? So if you see any constant or any power function, you can now find the derivative really quickly. You don't need to go back to the limit of the difference quotient. Okay, we've also got something called the constant multiple rule. And basically what it says is, if you've got a constant times a function where you know how to find the derivative, it's just going to be the constant times that derivative. Okay, it's kind of like ignoring the constant, kind of like we did with limits, finding the derivative, and then bring that constant back and use it as a multiple. Okay, so find the derivative of the function, then multiply it by the constant. So if we were doing this problem right here, technically this is what you'd do. You'd think of this as 5 times the derivative of x to the 4th, which would be 5 times, let's see, this is going to be 4x to the 3rd. So my answer is going to be 20x to the 3rd, right? Now, in reality, we don't do that. In reality, we just say, hey, multiply by the old exponent. That's going to be a 20. Reduce the exponent by 1. You get the same answer. This is technically the way you'd think about it. We're applying the constant multiple rule, but everybody just does this. So in this problem, all we're going to do is we're going to take the old exponent, multiply it. So we're going to have a negative 18 here, and we're going to have x to the 8th. End of story. It's that quick. Okay, are there any questions? Okay. All right, so then there's something called the sum and difference rule. So every one of the derivatives that we've been finding so far with these rules all just have one term. Well, if we have more than one term, whether we're adding or whether we're subtracting, doesn't make any difference. You can find the derivative of each piece. So if we have f of x equals u of x plus v of x, then the derivative of f would be u prime of x plus v prime of x. Or if we did it in differential notation, the derivative with respect to x of u plus v would be du dx, the derivative of u with respect to x, plus the derivative of v with respect to x. So the only reason why I'm writing this 2 different ways is just so you get used to the notation. It's not 2 separate rules. It's just different ways of writing the same thing. Again, this is prime notation. This is differential notation. Okay? Any questions there? Okay. This one I'm pretty darn sure you can follow. So we want to find the derivative. So just a really quick proof of this. If the derivative of f is this expression right here, the limit of the difference quotient, okay, we want to find from the definition what would the derivative of u of x plus v of x be. So we literally use u of x plus v of x as the function. So this is what we'd have. So f prime of x would be, this is going to be u of x plus h plus v of x plus h. There are the 2 terms that we'd plug x plus h into. Minus, now remember that second part you really ought to put in parentheses, just whatever we get when we plug in an x. So this would be u of x minus v of x. Whoops, all of that's over h, and I forgot to write the limit. Limit as h approaches 0. Okay, now, this one, if they gave you a problem like this, if they said prove the sum rule or the difference rule, this I'm hoping wouldn't be too bad. Does anybody see what we'd need to do to this? Ben says what?
Multiply it out.
Okay, let's multiply through. So let's distribute the negative. Oops, that should be a plus. So this is going to be the limit as h approaches 0. This is going to be u of x plus h minus v of x plus h. Whoops, that's plus. Then minus u of x minus v of x all over h. Ideas now? Right?
Multiply the u and the v with the x plus h.
Like distribute through here, is that what you're thinking of? Okay, so we want to be a little bit careful there. There aren't very many functions that distribute, so we couldn't write this as a u of x plus a u of h. So you got to be really careful there. It's kind of like signs don't distribute. You can't take the sine, like the sine of 30 plus 45 isn't the sine of 30 plus the sine of 45. Very few functions distribute like that. Okay? So I'm going to suggest we do this. How about we rewrite this in a little bit different way? So I'm going to come down here and I'm going to write limit as h approaches 0. I'm going to put the u's together, so this would be u of x plus h minus u of x, and then this is going to be plus v of x plus h minus v of x all over h. So I still have the same four terms, I've just written it differently. And then we're almost there. Your hint is, look at the starter question. We like this as one single fraction. But does it have to stay that way? It doesn't. We could break this up again using properties of fractions and the limit laws. We could break this into the limit as h approaches 0 of u of x plus h minus u of x over h plus the limit as h approaches 0 v of x plus h minus v of x over h. I didn't break it into four separate fractions. I broke it into these two over this one, which is okay, and these two over this one. If I were to add these two expressions together, they already have a common denominator, so they'd have an h in the denominator, and then I'd have all four of these terms up here. So does everybody agree that this is a legal way to rewrite this? Okay? And do you recognize this? And do you recognize that? What is this? That's the derivative of u. Okay? So this is u prime of x plus, what is this? V prime of x. Okay? Notice that we didn't rely on what the particular function was, any of the properties of the function that we had. All we were relying on was the definition of the derivative, properties of limits, and properties of fractions in order to figure that out. We broke it up so that it looked more familiar, so that we could see, hey, there's a derivative of u right here, and there's a derivative of v right here. Okay? And again, this works whether you're adding terms or subtracting terms. Okay? Any questions? Okay, then let's take a look at a couple of these, because they're literally this easy. Okay? I'm explaining why these things work. We've done a couple quick little proofs, but the rules are really simple to work with. If you've got three terms and you're adding them together, just use the rules that we've already learned and find the derivative of each piece separately and then either add them or subtract them, whatever it happens to be. So on this problem right here, we're finding the derivative of this term plus this term plus this term. So the derivative of 2x is, sorry, see that's bad when I give away the answer. This is like Jeopardy. What's the derivative of x squared? 2x. That's simple. What's the derivative of 2x? Let's think about that for just a second. What was the derivative of x? That was 1, so the derivative here would just be 2. If you wanted to think of it this way, the exponent is 1. Bring that down, it would be 1 times 2. What would our new exponent be? 0, and what's any number to the 0 power? That's going to be 1. So we'd get just a 2 here, and then this would be minus. I would just flat get this memorized because square roots come up so often. The derivative of a square root is 1 over 2 times that same square root. So this is going to be 1 over 2 times the square root of x. That's it. My gosh, can you imagine going through and finding the derivative from the definition on that function? And yet we just write it down there. I mean, I'm yapping and it took us less than a minute. Okay? So on this one right here, notice I've put a problem here. We see position, velocity, acceleration come up quite a bit. We talked about the relationship between position and velocity. Velocity is the derivative of position. So if this is the position function, and we normally denote that with an s, and I ask for v of t, this is literally saying, hey, if you know the position function, would you find the velocity function for me? So in other words, what's it saying to do to this? Find the derivative. So let's write down what the derivative would be. The derivative would be 20t cubed minus 6t squared. And that would be a 0, so I don't have to write it. That right there is the derivative. Okay? All right. Any questions there? They're that quick. They're that easy if you practice with them. You do have to know these really, really well. Okay? All right, next page. So whenever somebody says, hey, I'm working with the exponential, you don't have to say which one. Okay, once you get past like 1050, if somebody says the exponential function, it's the one with base e. E is so important. If we say we're working with an exponential and don't specify, that's the one we're working with. Okay? If you've got an exponential base e, its derivative is e to the x. So again, this is prime notation. If I said what's the derivative with respect to x of e to the x, it is e to the x. So the derivative of the exponential function is the exponential function itself. It doesn't change at all. It is the only function that's its own derivative. Well, non-trivial one. What would the derivative of 0 be?
0.
The derivative of 0 would be 0. Okay, but that's kind of a silly example. Okay. So I'm going to run through a really quick proof with this. It relies on a limit that we've seen once or twice before. So here's what we do. Our function is e to the x. So our derivative is going to be the limit as h approaches 0 of e to the x plus h minus e to the x over h. I then recognize that this can be rewritten as the limit as h approaches 0 of. Now again, we don't normally do this. We're normally interested in putting exponents together, not breaking them apart. But isn't this e to the x times e to the h minus e to the x over h? Isn't that the same thing? It is. And at this point, I can factor that out. So this gives me the limit as h approaches 0, e to the x, e to the h minus 1 over h. Everything okay algebraically here? Okay, now, what is the variable in the limit? H. So that means everything else, numbers, letters, whatever, we treat them like they are constants. So what is this right here? Is it a variable? Is it changing? Or is it a constant? It's a constant in the limit. So I can bring this out front using the constant multiple rule for limits, and I can find the limit as h approaches 0 of e to the h minus 1 over h. Now, this technique works with every single exponential. You can get it to something that looks like this. And does anybody recognize this limit right here? Okay, I think we've dealt with it at least once. This limit is 1. So the limit is e to the x times 1 or e to the x. So start out with the function e to the x, find its derivative using the definition, and you're going to get e to the x. Again, it's the only one of consequence that has that property. Okay? So years from now, you're going to remember what's today. Is today the 18th? 18th of September 2012. 20 years from now, somebody's going to say, hey, did you take calculus in high school, old man? And you're going to say, yeah, I took calculus. Do you remember anything? Most people remember 2 things from calculus. Okay, hopefully you remember more because I taught you, right? They remember how to find the derivative of a power function because that's so easy. Bring the exponent down, multiply that, reduce the exponent by 1. And they remember the derivative of the exponential. Okay? I'm going to make you memorize a sentence, a couple phrases that describe what calculus is, so hopefully you can do that. But there you go. Okay, so if you want to find the derivative with respect to x of 5e to the x, it's just 5e to the x. Done. And then we're finding the derivative with respect to x of this function right here. Derivative of negative 4e to the x is negative 4e to the x. Okay, now derivative of bx squared. Again, usually we use letters at the beginning of the alphabet to represent constants, so they could represent numbers, and letters at the end to represent variables. So we think of this just like we would a normal coefficient. So this would be, bring the exponent down and multiply it. That would be 2b and then x to the first. And what about the derivative of this? It's a constant, so its derivative is 0. I'll write it just to emphasize. Maybe I won't write it so vigorously. Okay? All right. Any questions? Okay, so what I'm hoping is all the stuff that we've gone over so far seems reasonably intuitive, okay? Once you get used to the power rule, that's easy to work with. The sum and difference rule, those should be pretty easy. Other than the derivative of the exponential function, hopefully they're like, okay, I can get used to that. That seems pretty reasonable. This is a little weird, okay? The, exponential basically is a pretty darn cool function, okay? So we really need to be good at finding the derivatives of lots of different functions, and it would be nice if they were all this easy, okay? They're not. So for example, it would be nice if you were finding the derivative of a quotient. You had one function on the top and one function on the bottom, and it was just, hey, find the derivative of the top, find the derivative of the bottom, and then divide them. It's not that simple, okay? And it's not very simple finding the product of two functions. We're going to find rules for those over the next couple days. We'll start that in 3.2. Okay? So for right now, all you have to rely on is the rules that we've gone over right here, the derivative of the exponential, okay, the constant, derivative of a power function, sum and difference rule, stuff like that. So everything has to be turned into one of those things. So right now, this is a function times another function. Well, we don't have the product rule yet. We're going to do that tomorrow. So we have to make this look like either an exponential, my gosh, I hope you don't find an exponential in there, a power function, a sum of power functions, or a big long polynomial, so that we can use the power function, the power rule, sum and difference rule, constant, stuff like that. So in order to find the derivative of this, we're going to have to distribute through, make a big long polynomial. So this is going to give me 3x cubed, let's see, minus 12x squared plus 2x minus 8x. So the function that I've got here, if I were to rewrite this in a form that I could, oh, is that a 2x squared? Thanks. 3x cubed minus 10x squared minus 8x. That's the function. So what's y prime? Right? Pretty cool, huh? Again, I'll say this one last time. Think about how long that would take to do it using the definition. I mean, that would take forever. Okay? All right, let's take a look at the next one. It's this function. It's a regular old polynomial divided by a square root function. It would be really nice if I could find the derivative of the top and then divide it by the derivative of the bottom. That is not how you find the derivative of quotients, though. It's not that simple. So I need to make this something that looks like a rule that we've already learned. Yeah?
Since the square root of x is on the bottom, you could use negative powers to bring it up.
Very good. Okay, so that's the trick there. Generally speaking, exponents are easier to work with than roots. So let's write that as an exponent. Let's write it as a power, because if it's a power, I can use the power rule to differentiate it. So I'm going to rewrite this as 5x to the 7th plus 2x, and this is going to be x to the 1/2. It's still a quotient, though, so I've got to somehow change it into sums and differences in a power function or something like that. So I'm going to do this. I'm going to write this as 5x to the 7th over x to the 1/2 plus 2x over x to the 1/2. And then if I did move this up like Ryan was suggesting, what happens to the exponent when I move it on the top? It becomes x to the negative 1/2, x to the negative 1/2, and then I add these together. So here's what I'm really trying to find the derivative of. I'm trying to find the derivative of, this would be 5x to the, let's see, 7 minus 1/2 is 6 1/2, so this would be 13 halves. And this is going to be plus 2x to the, well, this would just be x to the 1/2, right? That is another way to write f of x. So if I say what's the derivative, what's f prime of x, this would be, let's see, if I multiply by the exponent, that's going to be 65 halves. If I reduce the exponent by 1, that's reducing it by 2 over 2, so that's going to be 11, whoops, make that look right, 11 halves. And then this one's going to be a half times 2, so that's going to be a 1. And this is going to be reduced by 1, so that's going to be x to the negative 1/2. And would I leave it like this? Is this simplified to a reasonable degree? Okay, again, if you had to use it again, that should be your key whether or not you've simplified. If you had to plug something in, would you want to plug it into this, or would you want to plug it into something that looks like this? 65 halves, and then this would be the square root of x raised to the 11th, and then this would be plus 1 over the square root of x. That probably would be a better way to write it. Okay? Both are mathematically correct. Is everybody listening? On a test, if you can't think of how to simplify it, don't screw things up. If you did this correct, and this is mathematically correct, don't do something to make it mathematically incorrect. So don't make an algebra mistake when you're simplifying and screw up your correct answer. Everybody got that? So if you didn't know how to do this, which hopefully you do, you'd want to just leave it like this. Okay? All right. Any questions? Okay. So let's take a look at something called higher order derivatives. We mentioned these the other day, so I want to be a little bit more clear and give you some quick examples to show that finding the derivative of the derivative of the derivative, finding the derivative multiple times doesn't always have to be difficult like it was in the last section. It can be pretty easy once you know these rules. So these are called different orders of derivatives. So this is the first derivative, second, third, and at this point we say y prime, y double prime, y triple prime. This is the fourth order derivative, then it would be fifth order, sixth order, and so forth. We stop writing primes and we write in parentheses what order derivative it is. Or if we say it over here, remember how to say this in differential notation? dy dx, d squared y dx squared, d cubed y dx cubed, d to the fourth y dx to the fourth. Or again, at this point, once you go past 3, we say what the order of the derivative. Fourth derivative of y with respect to x. Okay? Any questions there? So let's write down the first derivative. First derivative is 20x to the third minus 6x squared. Just checking to see if you're paying attention. 60x squared minus 12x. 120x minus 12. 120. And for the heck of it, what would the fifth derivative be? 0. And the sixth? Everyone after that's going to be a 0. That would happen with a power function. If you've got a polynomial, eventually you're going to be able to differentiate it to 0. Okay, are there any questions? Easy enough? Okay, all right, so let's take a quick look at these. Remember what I said about the square root function. It's one you ought to memorize because it comes up so often. The derivative of a square root, now I'm going to qualify this a little bit. We're going to find later on how to do more complicated derivatives of square roots. Okay, but for the time being, you can remember it this way. It's just 1 over 2 times that same square root. The derivative of a square root is 1 over 2 times that same square root. So, didn't we do the cube root already? Okay, that would be x to the 1/3. So that's going to be 1/3 x to the negative 2/3. So if I wrote that, it would be this. 1 over 3 cube root of x squared. There's that derivative. Let's do the fourth root. X to the 1/4. That's going to be 1/4 x to the negative 3/4. So if I wrote its derivative, that's going to be 1 over 4, fourth root, x cubed. Could we write the derivative of the fifth root of x without going through that process? Do you see a pattern? Ryan?
First off, you see the little square root, the little number that tells you what.
It's called an index. So this is the radical, and that's the index. It tells us what root we're after.
So you take the index and put it over 1, and then you times it again by the
Okay. So it's going to be 1 over 5 What root?
Root 5.
Fifth root. X to the fourth. Okay? So this is a square root. It's 1 over 2 square root, and the power on the x is 1 less than the index. So this is 1 over 3 cube root x squared, 1 over 4 fourth root x cubed, 1 over 5 fifth root x to the fourth. And if we were to do this one right here, 1 over 6 sixth root of x to the fifth. Okay? Nice little pattern there. These don't come up very often, but they should be pretty quick to do. It's not like you have to memorize these. I would get that one memorized for sure. Maybe the cube root. Okay, but the other ones, they're just kind of an interesting pattern that comes up. Okay, any questions there? Okay, this may or may not come up in this textbook, but it typically does in a lot of books. And if you go on in math, I guarantee you're going to see these words. It says blank and blank are two words that can be used in place of the word perpendicular. I think if you had me for trigonometry, I think I mentioned at least one of these words. Anybody remember? Okay. So the word normal and orthogonal. Okay? Normal and orthogonal. So if somebody says, hey, I've got the normal line or I've got the orthogonal line, what it means is it's perpendicular to the curve. So we're used to doing stuff like this. We're used to finding the tangent line. So if that's the tangent line, it's right in line with the curve. The normal line or the orthogonal line would look something like this. It would meet at that same point of tangency, but it would be perpendicular to the tangent instead of parallel with the tangent, parallel with the curve, if you will. Does that make sense? Okay, so let's take a look at the last problem. And before I do the last problem, these are the problems that I'd like you to add to the assignment. There really aren't that many to begin with, and I picked ones that I think would be much more useful down the road to give you some good middle-of-the-road practice. And then if you would make sure you do problem number 9 before class tomorrow. It's similar to one that we've done in class. It shouldn't be too hard, but I'm going to use number 9 in tomorrow's lecture. Okay, so if you'd make sure that you do that. And then just a general word of encouragement. Most of these take, the rules that we're going to be learning in this chapter, they take a long time to get used to using. We've gone over some general ideas and you might have a good feel for it, but you need to see how to use those rules in lots of different situations so you recognize, oh, this is just a sum of some functions. I can find the derivative of each piece. Okay? This is just an exponential. Okay? It's got a constant in front of it. It's just going to be the constant times the exponential. Okay? So just keep in mind that they do take a lot of practice before you get really good at them. So, last problem here. It says, find the equation of the tangent line and the normal line for g of x equals 2e to the x minus 3 at x equals 0. Then graph the function, the tangent, and the normal lines. So, let's see. It says come up with a tangent line and a normal line. Well, let's focus on this for right now. We're good at finding tangent lines. What do we need in order to write the equation of the tangent line? We need a slope and a point. So they didn't give us a complete point or a complete slope, but we've got enough information we can figure that out. So here's our point. Our point is going to be 0, comma. Let's see what we get when we plug in a 0. If you plug in a 0, you get 1 times 2 minus 1. So this is 0, negative 1. Correct me if I'm wrong. Okay? And then we need a slope. Or in other words, we need the derivative. So g prime of x is, let's see, what's the derivative of 2e to the x minus 3? 2e to the x. Derivative of the exponential function is the exponential itself. It's got a constant out front. We use the constant multiple rule. It just hangs around there, multiplies by the derivative after we get that. And the derivative of a constant is 0. So here's the function that will give us the slope. We want to find g prime of 0. And what is g prime of 0? G prime of 0 is 2. Okay? So here's our point and here's our slope. All we have to do is write the equation of the tangent. So the tangent is y minus 1, so that would be y plus 1. Slope is 2, and then x minus 0. If you want to clean that up, you can. So there is the tangent line. Now here's the cool thing. If we want to find the normal line, we want, let's see, how do we make it perpendicular?
Opposite reciprocal.
Opposite reciprocal, right? So we're going to take this slope. If it's sloped at 2, we want a slope that goes this way. So it needs to be a negative slope and a lot smaller in this particular case. So opposite reciprocal. Whoa, what happened here? That's why you were laughing. All right, that's better. Okay, so now let's write down the normal line. It's going to be exactly the same because it goes through the same point, right? Except for this needs to be negative 1/2 x minus 0. Be really careful. Okay? So here's what we're going to do. In y1, we're going to put the function 2e to the x minus 3. In y2, we're going to put the tangent line, and correct me if I'm wrong, but the tangent line is 2x minus 1. And in y3, we're going to put the normal line, and that's going to be negative 1/2. Whoa, where'd we go there? X minus 1. So what we should see when we graph this, we should see something about like this. Okay? So let's see what we've got here. Two e to the x minus 3, 2x minus 1, and the other one was negative 1/2 x minus 1. Right? And I'm gonna hit zoom 4. I'm gonna hit the decimal window just because that's a nice square window. Hopefully things look like they're perpendicular. Okay, there's the original graph. That looks pretty good. There's the tangent line, and here comes the normal line. And that sure looks like it's a right angle. Okay? Any questions? Okay. 2.8 technically is due tomorrow. Hopefully you were done with that today, except for some of the ridiculous proofs at the end. If you would really try, I would really appreciate it, and you will appreciate it, if you're done with 3.1 when you come to class tomorrow. Tomorrow we're going to learn 2 rules. They're the first complicated differentiation rules. Okay, product rule and quotient rule. How do you find the derivative of 2 functions that are being multiplied together? And how do you find the derivative of 2 functions that are being divided? Okay, they are far less than intuitive. In fact, they're pretty counterintuitive.